In the last tutorial, we used the flux.jl package to build an artificial neural network model that could read handwritten digits from the MNIST dataset. But because we spent all of our time just writing the code, we didn't have much time to go through the concepts behind the code. In this tutorial, we will revisit that code and step through it to gain some intuition regarding artificial neural networks. So, are neural networks as complicated as they seem? Well, let's find out. Welcome to Julia for Talented Amateurs, where I make wholesome Julia tutorials for talented amateurs everywhere. I am your host, the Dabbling Doggo.
I dabble.
Before we can talk about artificial neural networks, we need to go back and get a refresher on logistic regression. Back in episode 503, we learned about logistic regression. In that episode, we took some input data and passed it through a model that returned an output between 0 and 1, which we used for binary classification purposes. That model contained a linear part as well as a non-linear part. The linear part was just the equation for a straight line. Rather than using the terms slope and y-intercept, we call them parameters, θ1 and θ0. Because our data wasn't linearly separable, we passed this linear equation through the nonlinear logistic function. By changing the value of the parameters, we discovered that we could change the shape of the logistic curve to best fit our data, so that we could use it to make predictions. In order to change the values of the parameters, we first had to define a cost function, and then come up with a method to minimize the value of that cost function. By taking the partial derivative of the cost function, we could determine both the direction and magnitude of the change required to reduce the cost. We also set a learning rate so that the changes made to the parameters weren't too slow or too fast in order to ensure that our process could locate the minimum value. We call this optimization algorithm batch gradient descent, and we repeated this process using a for loop over multiple epochs. Hopefully, this process sounds familiar, because the process that I just described is almost identical for both logistic regression and for artificial neural networks. You can think of logistic regression as a special case of an artificial neural network. Artificial neural networks are made up of a collection of neurons. Each neuron is like a mini logistic regression model. The difference is that the artificial neural network connects multiple neurons together in order to create a more sophisticated model. Let's step through the code from the last tutorial, and I'll pause periodically to provide some insights as to what's going on behind the code. I am, of course, assuming that you've watched the last tutorial. In the VS Code Explorer panel, open the sl_ann.jl file from the tutorial 05x08 folder by double-clicking on it. Start the Julia REPL by using Alt-J, then Alt-O. For this tutorial, I'm going to dock the REPL panel next to my editor. In the REPL, change the present working directory to the tutorial 05x08 directory. Enter the package REPL by hitting the closing square bracket. Activate the directory. Exit the package REPL by hitting backspace. Before we start going through the code, I need to acknowledge the developer of the flux.jl package. The flux.jl package was created by Mike Innes, who's like a celebrity within the Julia community. There are many YouTube videos featuring Mike Innes and the flux.jl package. If you go to Julia Hub, the flux.jl package is listed near the top of the list, with over 3,500 stars as of this recording. You can show your appreciation to the developer and all of the contributors by going to the GitHub page for flux.jl and leaving them a star. In the editor, start executing the lines of code until you define the model architecture. If you look in the REPL, you'll see an output stating there are 25,450 parameters. 25,120 for the first dense layer, and 330 for the second dense layer. So how did Flux come up with those figures? If we go back to the diagram of our model, there are 784 nodes in the first column and 32 nodes in the second column. Using 784 and 32 with a dense constructor creates a so-called dense layer with 784 nodes as inputs and 32 nodes as outputs. Each connecting edge contains a parameter, and each output node also contains a parameter. So if you look at the first node in the first column, that node is connected to 32 nodes in the second column. 32 times 784 is 25,088 parameters. Since each node in the second column also contains a parameter, we need to add 32. So the total number of parameters in this dense layer is 25,120, which is what the REPL output shows. Now, if we look at the second column and the third column, there are 32 nodes as inputs and 10 nodes as outputs, which is the second dense layer. The chain constructor just connects those two dense layers together. The first node in the second column is connected to 10 nodes. 10 times 32 is 320. Since each node in the third column also contains a parameter, we need to add 10. So the total is 330 parameters for the second dense layer. So if you add the 25,120 parameters from the first dense layer and the 330 parameters from the second dense layer, you get 25,450 total parameters, which is what the REPL output shows. That's a lot of parameters, but as you can see, the majority of the parameters are in the first dense layer. Now, what are these parameters? The parameters along the edges are called the weight, and the parameters in the output nodes are called the bias. The weight is equivalent to theta 1 or the slope, and the bias is equivalent to theta 0 or the y-intercept. These parameters are used in the linear part of this model, which is written Wx plus b. I'm not sure why the names of the parameters were changed from theta 1 and theta 0 to weights and biases, but it seems like a lot of terms have been renamed or rebranded for artificial neural networks. Another example of a name change is the logistic function. For logistic regression, we pass the formula for a straight line through the logistic function in order to create a nonlinear function with parameters that we could use to reshape the curve. For artificial neural networks, the logistic function is called the sigmoid function. It's the exact same thing with a different name. In this new world, the sigmoid function is an example of something called an activation function. An activation function is the term given to the nonlinear portion of the artificial neural network model. The sigmoid function is one example of an activation function, but there are several other nonlinear functions used with neural networks. The activation function that we used in our model is called ReLU, which is short for Rectified Linear Unit. ReLU is commonly used for multi-class classification problems. Here's a diagram of the ReLU function. So when x is negative, y is 0. And when x is positive, y just equals x. Just like in logistic regression, the linear portion of the model is passed through the nonlinear portion of the model. For the final output, we use the softmax function. The softmax function is a generalization of the logistic function to multiple dimensions. Using the softmax function returns values that are between 0 and 1 for each element in the dimension, and then normalizes the dimension so the values add up to 100%. Before we leave this model, let's take a closer look at the math. The process of making calculations going from left to right in this diagram is called forward propagation. The first column contains the values from the 784 by 1 image sample, which are floating point numbers with values ranging from 0 to 1. Looking at the first node in the first column, that value is multiplied by a weight and added to a bias. Then that value is passed through the ReLU function. So this math needs to be repeated 32 times for each node in the second column. Then this math needs to be repeated 784 times for each node in the first column, and then 60,000 more times for every sample. That's a lot of calculations. So this model isn't actually performing all of those calculations one by one. Instead, it's using linear algebra to perform those calculations in parallel. Rather than going through the actual math, let's go through some shape analysis to see what's going on. You don't need to know linear algebra in order to use the flux.jl package, but it's helpful if you want a deeper understanding of what's going on under the hood. In the first dense layer for column 1 and column 2, the weights, or W, are contained in a matrix with 32 rows and 784 columns. The inputs, or X, are contained in a matrix with 784 rows and 60,000 columns. By using linear algebra, W times X results in a matrix with 32 rows and 60,000 columns. Now you know why we had to flatten the input data into a 784 by 60,000 matrix. The biases, or B, are contained in a column vector with 32 rows. Since we need to add this column vector to each column in the resulting W times X matrix, the model uses broadcasting. As a result, there is no change to the shape of the 32 by 60,000 matrix. This 32 by 60,000 matrix is then passed through the ReLU function, which also doesn't change the shape. This resulting 32 by 60,000 matrix becomes the input matrix for the second dense layer. The weights for the second dense layer for column 2 and column 3 are contained in a matrix with 10 rows and 32 columns. We just calculated the new X, which is a 32 by 60,000 matrix. So W times X is a matrix with 10 rows and 60,000 columns. The biases for the second dense layer are contained in a column vector with 10 rows. Again, we use broadcasting to add this column vector to each column in the W times X matrix. So the result is the same 10 by 60,000 matrix. This result is then passed through the softmax function, which results in output values between 0 and 1, with each column adding up to 100%, but without any changes to the matrix shape. And now you know why we converted the labels into a one-hot matrix that is 10 by 60,000. And you also know how our model converted a 784 by 60,000 input matrix into a 10 by 60,000 output matrix. Let's move on to the loss function. In artificial neural networks, the term loss function is used rather than cost function. They're essentially the same thing, but according to the Stanford course, the term loss function is used when there's only one example in a batch, and the term cost function is used when there are multiple examples in a batch. In the flux.jl package, the term loss function is used for the objective function. In any event, there are many different loss functions that you can use to train your model. The flux.jl documentation has a section dedicated to the different loss functions that it supports. In our model, we use the cross-entropy loss function, which is often used for multi-class classification problems. Similar to the way our cost function worked with logistic regression, the cross-entropy loss function rewards correct predictions and punishes incorrect predictions. So all your computer needs to do is to adjust the parameters until it finds a minimum value for this loss function. Let's take a look at how those parameters were initialized by Flux. According to the Flux documentation, the params function creates a params object that points to its trainable parameters. This params object is required for the training utility function. The parameters are stored in memory in 4 separate arrays, which you can view in the REPL by using index numbers. These are the weights for the first dense layer. As you can see, the weights are contained in a 32 by 784 matrix, just like we drew in our shape diagram. The values appear to be random, but let's take a look at the minimum and maximum values. So the values range from approximately negative 0.09 to positive 0.09, which is a fairly tight range. These are the biases for the first dense layer. As you can see, they're contained in a column vector with 32 rows. The biases are all initialized with a value of 0. These are the weights for the second dense layer. As you can see, the values are contained in a 10 by 32 matrix. Again, let's take a look at the minimum and maximum values. So the values range from approximately negative 0.4 to positive 0.4, which is still a tight range, but much wider than the range for the first dense layer. And finally, these are the biases for the second dense layer. As you can see, the values are all 0, and they're stored in a column vector with 10 rows. So, what are the key takeaways? The shape of the parameters are all consistent with the shape diagrams that we drew earlier. The values of the biases are initialized at 0. The value of the weights are initialized using some methodology using both positive and negative random numbers, within a range that depends on the number of nodes in the dense layer. To be honest, I'm not exactly sure how the Flux package is initializing these values. In any event, these are the parameters that we need to update in order to minimize the value of the loss function. In order to minimize the value of the loss function, we need an optimization algorithm that will determine how those parameters will be updated. In the past, we've used batch gradient descents, but there are many different types of optimization algorithms. You can view the optimizers supported by the flux.jl package in the Flux documentation. In Flux, the optimizer called descent is the classic gradient optimizer. Although batch gradient descent is an excellent optimizer, it is computationally expensive, so it may take a long time to train an artificial neural network model. Another common optimizer is called momentum, which looks back at prior updates in order to calculate an acceleration for future updates. The optimizer that we used in our model is called ADAM, which is short for Adaptive Moment Estimation. The ADAM optimizer is a version of stochastic gradient descent, meaning that it calculates a gradient based on a random subset of the data rather than using the entire batch. In addition, the ADAM optimizer starts with an initial learning rate, but decays that learning rate over time, which allows it to reach its objective faster than classic gradient descent. On a side note, the learning rate is another example where the name has been changed for some reason. In prior tutorials, we used the lowercase Greek letter alpha for the learning rate. For artificial neural networks, you'll see the learning rate referred to by the lowercase Greek letter eta. Again, I'm not sure why they changed the name, but it's the same thing. So we are now ready to retrain our model. The only peculiar thing about this training utility is that you need to enter the training and testing data in the third argument in a very specific data structure. That's a scalar containing a tuple. The first element of the tuple is a 784 by 60,000 matrix containing the input data, and the second element of the tuple is the 10 by 60,000 one-hot matrix containing the label data. This training utility function provided by Flux simplifies an otherwise complex training process. In order to update the parameters, the training process uses something called backpropagation. So this backpropagation process is completely invisible to the user, so knowledge of it is not required to use the flux.jl package. I understand the basic concept behind backpropagation, but to be honest, I don't understand all of the math, so I haven't been able to reconstruct it manually on my own. At a very high level, it's doing the same thing that we've done in the past. It's using calculus to take a derivative of the loss function in order to calculate both the direction and the magnitude of the updates required for the parameters in order to minimize the value of the loss function. The difference here is that the loss function for an artificial neural network has a very complex surface in multidimensional space, so it's impossible to visualize. Backpropagation starts at the end of the process with the loss function, and then moves backwards in order to calculate the updates to the parameters. After all of the parameters have been updated, the model recalculates a loss by using forward propagation, and then the process keeps repeating until you tell it to stop. Now that we've trained our model, Let's take another look at the parameters. So the weight for the first dense layer is still a 32 by 784 matrix, but the range of values is much wider, going from approximately negative 4.17 to positive 4.15. The biases for the first dense layer are no longer just zeros. Instead, it contains a range of values from negative 0.46 to positive 0.42. The weights for the second dense layer tell a similar story as the weights in the first dense layer. The values are still contained inside a 10 by 32 matrix, but the values now range from negative 3.3 to positive 2.2. Finally, the biases for the second dense layer are no longer just zeros. Instead, the values range from approximately negative 0.3 to positive 0.2. You may be interested in saving these parameters to disk, so you won't need to retrain your model every time you want to use it. The Flex documentation has a section called Saving and Loading Models, where you can learn how to save your parameters to disk and how to load them from disk. Now that we know a little more about the concepts behind the code, let's take another look at the diagram of our model. As we noted earlier, all of those edges contain a parameter called a weight. You can think of those weights as the strength of the connection between the nodes. Also, as noted earlier, the nodes in the second column and in the third column contain a parameter called a bias. You can think of the bias as a dial that fine-tunes the outputs, just like the y-intercept does for a straight line. The y-intercept doesn't have any impact on the shape of the line, but it determines where to place that line in space. When you pass the weight and the bias through the ReLU activation function, the result will either be 0 for negative values of wx plus b, or it will just be wx plus b. Now you know why it's called an activation function, because it determines if that particular neuron will be activated to send a signal to neurons further downstream. You can think of that second column as an abstraction of the input data. Having 784 inputs may be too difficult for your computer to comprehend all at once, but having an abstract view of it using only 32 of the most salient input features makes it easier for your computer to find patterns in the data, which ultimately helps it make more accurate predictions. The number 32 is somewhat arbitrary. There's no established method for choosing the number of intermediate neurons, so feel free to play around with different values to see if you can improve the accuracy score. I'm clearly no expert in the subject, and you're learning the subject as I'm learning it. Sadly, this concludes my coverage of artificial neural networks for this series. But for those of you who would like to pursue this subject further, here are some additional resources provided by folks who are smarter than me. All of the links are in the description below. There are a couple of lectures in the Stanford Machine Learning course that cover neural networks, so be sure to check them out if you want a deep dive into neural networks. Huda Nassar also has a tutorial on neural networks in her data science playlist. There have been some changes to Flux since she made her video, but it's still a good tutorial, so you may want to check that out. A lot of the code that I used came from the Flux Model Zoo, which contains a collection of Julia code for various deep learning models, so that's another good resource. And of course, there's the Neural Networks playlist from 3 Blue 1 Brown. If you're subscribed to my channel, I'm assuming that you're subscribed to 3 Blue 1 Brown as well. He published his Neural Networks playlist back in 2017, so I'm only like 5 years behind. I'm sure there are many more resources that I'm leaving out, but these resources should keep you busy for a while. Well, that's all for today. If you made it this far, congratulations! If you enjoyed this video and you feel like you learned something new, please give it a thumbs up. For more wholesome Julia tutorials, please be sure to subscribe and hit that bell. If you like what I do, then please consider joining and becoming a channel member. New tutorials are posted on Sundays/Mondays. Thanks for watching, and I'll see you in the next video.